Hello, guys. We're going to be covering Parikh's theorem. My name is Parikh.
My name's Aryan.
And this is Aarsh Patel.
During this presentation, I'm going to be first introducing Parikh's theorem and giving all the important terminology to understand the proof of Parikh's theorem.
I will be giving an overview of the simplified proof for Parikh's theorem.
And I will be showing the implications and use cases of Parikh's theorem.
Now, what is Parikh's theorem? Parikh's theorem was proven by Rohit Parikh 66 years ago in 1961. Basically, if we take the number of occurrences of each terminal in a CFL, then it will be identical to some regular language. And every CFL language's Parikh image is semilinear. So for example, if we take the regular language 1, 0 star, it is equivalent to the CFL 0 to the power of n, 1 to the power of n under Parikh's theorem. Now, before we get into the proof, we will understand some important terminology required to uncover this proof. First, we have Parikh's image, and the notation of Parikh image is psi of W over the word W. So it is the Parikh image of W over its alphabet sigma, and a Parikh image of W maps all the characters in the alphabet to the number of occurrences in W. So for example, these two words have the same Parikh image because they have the same number of A's, B's, and C's respectively. Now, next we have letter equivalence. And a letter equivalence is a set of words that have the same number of occurrences of each symbol. So basically, if two words have the same Parikh image, they are letter equivalent. Next, we have linear sets. And a linear set is a subset of the natural number to the power of k. So basically, it is a linear combination of defined vectors. So for example, this linear set will produce the set of vectors containing 0, 0, 1, 1, 1, 0, 1, 1, 1, 2, 2, 2, 3, 3, 2, 4, 4, and so on as we alter the number the assignments of K1 and K2, which are also natural numbers. Then we have semilinear sets, and a semilinear set is a union of finitely many linear sets. So if we have n linear sets defined, then taking the union of all those n linear sets is a semilinear set. Next, we have regular set, and a regular set is a set that represents the value of a regular expression. It has similar properties of a regular language, which basically means that it is closed under union, intersection, complement, and difference. So for example, the regular set R is a regular set because it represents the value of the regular expression 1, 1 star. And last, we have strong pumping lemma. And the strong pumping lemma is a pumping lemma where the pumping length is p to the power of k instead of p. And we take advantage of a non-terminal a inside of the language that produces derivations of words in the language greater than or equal to, with length greater than or equal to p to the power of k.
I will finally take you through the simplified proof of Parikh's theorem. So first, I will define the relevant terms and notation that we would use for the proof. So firstly, given a context-free language L, let G1 be the context-free grammar that generates this language, and let P be the pumping length of G. So if we define U to be any subset of V with K non-terminals consisting of the start symbol S, then we can define L sub U as the set of words in CFL L such that each word can be derived using every non-terminal in U at least once and no other non-terminals. Since the CFL L is a union of L sub U, for all U, we can reduce the proof to proving that the Parikh image of L sub U is equal to the Parikh image of some regular set D, and the Parikh image of L sub U is semilinear. So we can use FG star to be such a regular set D, where F is defined as a set of all words in L sub U such that each word has length less than P raised to K, and G is defined as a set of terminals Vx such that for an existing repeated non-terminal A, there is a subderivation such that A yields Vax. Thus, I will be proving that the Parikh image of L sub U is equal to the Parikh image of Fg star for K non-terminals in U. So the basic idea of this proof is that in every direction, I will prove the trivial case first, and then prove the difficult case by inductively reducing it to the trivial case. So this proof will go in two directions. The first direction is proving that the Parikh image of L sub U is a subset of the Parikh image of Fg star, and the second direction is proving that the Parikh image of Fg star is a subset of the Parikh image of L sub U. So firstly, to prove the first direction, we first consider any string z in L sub u, and first consider the trivial case, which is that if the length of z is less than p raised to k. And then in this case, by the definition of f, z is in f, and since f is a subset of fg star, we can conclude that z is also in fg star, and its Parikh image is in the Parikh image of fg star as well. And now for the difficult case is that if the length of z is greater than p raised to k, greater than or equal to p raised to k, then since z also belongs to L sub u, then by definition of L sub u and the strong pumping lemma, this implies that there is a derivation of z by g by g1 using only and every non-terminal in u of the following form. We can see that the derivation has at least one repeated non-terminal a and k corresponding subderivations of the form a yields v sub I a x sub I. So this means that deleting any such derivation for repeated non-terminal a from this derivation would give a feasible derivation of z dash of shorter length than z, but the resulting derivation still uses every non-terminal in u at least once and no other non-terminals. So we derive shorter z dash that is an element of L sub u. So the strong pumping lemma suggests that while the length of z is greater than or equal to p raised to k, then there will always be a subderivation of form b yields v sub I b x sub I that can be deleted. Thus, while the length of z dash is greater than or equal to p raised to k, then we can inductively delete a subderivation that repeats a non-terminal from every successively shorter derivation of z dash until we finally obtain a derivation of z dash such that the length of z dash is less than p raised to k. After every such inductive step, z dash will always be an element of L sub u, as we showed in the last slide. Thus, z dash satisfies the condition for the proof trivial case, and we can apply it directly to conclude that z dash is an fg star. Since z can be rearranged as z dash concatenated with all such deleted v sub I x sub I at the end, the Parikh images are equal by letter equivalence. However, since z dash belongs to fg star and the remainder of the rearranged string is in g star, the rearranged string as a whole belongs to fg star. Thus, we can conclude that the Parikh image of z is also an element of the Parikh image of fg star. This concludes the first direction of the proof. Now, for the second direction, we will consider any string z in fg star, and first consider the trivial case, which is that if z is in f, then by definition of f, z also belongs to L sub u. So the Parikh image of z belongs to the Parikh image of L sub u, hence proved. And now for the difficult case is that if z is not in f, then this implies that z can be expressed as z dash vx, where z dash is an fg star and vx belongs to g. Thus, in this way, while z dash is not in f, we can inductively split successive z dash in fg star until we finally obtain z dash that belongs to f. Then we can directly apply the proof trivial case to conclude that z dash belongs to L sub u. By the definition of g, for any v sub I, x sub I, and g abstracted from z, we can add corresponding subderivation a yields v sub I, a x sub I to the derivation of z dash. So z dash is in L sub u, the resulting derivation from each addition will thus still only use every non-terminal in u. Therefore, by adding all such derivations, we derive z double dash that still belongs to L sub u. So the Parikh image of z double dash is an element of the Parikh image of L sub u. However, by the letter equivalence of z and z double dash, we can conclude that the Parikh image of z is also an element of the Parikh image of L sub u. This concludes the proof for the second and final direction.
Let's circle back and conclude the proof. We initially wanted to prove that CFLs are equivalent to regular languages if we ignore order. This is equivalent to saying that there exists a regular language R such that the Parikh image of the CFL equals the Parikh image of R, and we have shown that the Parikh image of L sub u equals the Parikh image of fg star. Now we need to show that fg star is regular and the Parikh image of L equals the Parikh image of some regular language. Now, due to the definition of fg star, the Parikh image of fg star can be classified as a semilinear set, and we will also claim that a semilinear set is equivalent to the Parikh image of some regular language. As a result, we can use these claims to see that fg star is in fact a regular language. Now, the proof for these claims can be seen. Unfortunately, due to time constraints, we will be unable to cover them, and we will assume that these claims hold true. Now, we need to show that the Parikh image of L equals the Parikh image of a regular language. Since L is simply the union of L sub u, and since fg star is regular, and regular languages are closed under union, we can see that the Parikh image of L equals the Parikh image of the union of fg star, which is a regular language. Thus, we have completed the proof of Parikh's theorem. Now, one implication of Parikh's theorem is that it allows us to easily check if a word is not within a CFL. The long way would mean we would have to construct a PDA and run it on input W. Instead, we can calculate the Parikh image of W and check to see if it is not in the Parikh image of the CFL. If it is not, then W is not in the CFL. Secondly, we can use Parikh's theorem to easily prove that a CFL over a singleton alphabet is regular. This type of CFL implicitly has no ordering. For instance, a string over the unary alphabet A of length 5 has only one unique Parikh image. Parikh's theorem claims that by ignoring ordering within a CFL, we create a regular language. Well, since this CFL already has no ordering, it is equivalent to a regular language. That was all for our presentation. Here you can see our sources. In addition to the paper, we also use secondary sources to better understand Parikh's theorem. Lastly, we would like to thank all the TAs and Jack for an incredible semester. And we want to thank Professor Galil for his enthusiasm in teaching us automata. Thank you and goodbye.